Okay, welcome back to our lectures. So in this video, actually we will see the Miller-Bravis indices. In the previous classes, we have seen how to draw a particular plane using a Miller indices, and specifically speaking, we have seen it for the cubic structures. But in the present class we will see actually just today I will give an outline only about the hexagonal close-back structures. It is not done as in the previous cubic structures. It is little bit complex also. Here I am not going to explain since it is somewhat beyond the scope of the syllabus and it's a vast topic. So those interested can watch this YouTube link. There's a clear and specific explanation is there by Professor Ratnakumar of IIT Madras. So just an outline. So we say about an outline. This is a hexagonal close pack structure. Here we have like various plane, like the top is known as the C plane and the side is known as M plane. And actually here we have four directions, like three base directions and one vertical height. Okay, but in previous one actually we have taken three indices, but here we will take four indices. Okay, totally four indices are there, which is named as H, K, I and L, and this system is known as this representation is known as a Miller-Bravis index system. It is basically a four-axis system. So for the time being, just understand this concept, and those who need detailed explanation can see this video. Okay, now next is the significance of this Miller indices. Why we are using the Miller index in material science? Okay. Material science, it's important to have a notation system for atomic planes, since this plane influence these properties. Okay, like in the last class we have seen how these atoms are represented. Like for example, if we need to specifically point out an atom. Okay, we don't know, we can't say it lies in this area. So in order to specify the position of that atom, we use this Miller index, and it is in turn it is very well applied to optical properties, to study the optical properties, the reactivity, the surface tension, and some dislocations, which we will see towards the last part of module 2. Okay, now we are moving to another important area, like the atomic densities. Basically, the density, we know the mass per unit volume, but here in the atomic level we will consider the number of atom lies on a specific line or a plane. Okay, let us see this one. The atomic densities are widely classified into two. The first is a linear density and second one is a planar density. Okay, the linear density is given by this equation, that is the number of atoms centered on a direction vector. If we consider a vector and if we are seeing how many atoms lies on that vector or in that direction, divided by the length of that vector or the length of direction vector. Coming to the planar density, we will see, or we will use this particular equation, that is the number of atoms centered or lie on a plane by the area of that particular plane. Okay. let us go deep into this one. But before that, like the properties which in general depend on these two densities, that is linear density and the planar density. Okay. The first one is the speed of sound along the direction. Okay. And the slip formation. Slip formation is in the sense that okay, this is the slip. Slip is some deformation which is actually occurring the within the our crystal structure. Due to slip, actually some layer, some atomic layers will deform from one position to another. And like we will explain this slip and all in terms of the linear or planar density, because this slip occurs along a line or a plane, particular plane. Okay, so we will see that like the slip occurs on planes which have the greatest density. Whichever place we have the greatest density, that means number of atoms are more. So along that direction, actually the slip occurs. So to identify this phenomena, that the slip and all, we uses these two descriptions, that is linear and planar density. Okay, now this is a problem. Here we want to calculate the linear density of aluminum in this particular direction. Okay, 110, and the edge length of a FCC aluminum crystal lattice is also given. I request everyone to pause the video at this moment and just try whether you can do it with your concepts you have studied, because you already studied what is an FCC structure and what is the edge length is also given. So you can draw this direction. This direction is also known to you, so you can just try this one and find out. Okay, the solution, this is the solution. We know very well that, and a particular direction is given, and here the direction given is okay, here the direction which is given is 110, and the edge length of the this particular FCC is also given. So the edge length means this one A, which is equal to 0.405 nanometer. And what we need to find is that we need to find a particular the linear density along 110 direction. This 110 direction means that this one means towards the x-axis, another second one means towards the y-axis, and 0 means no direction along x-axis. So as satisfy 1 we will draw in this direction. Okay, I think we have completed all these things in the previous slides. If you have any doubt, just go and check the video and ensure that you have thoroughly studied the directions. And coming back, like we need to find this particular distance, that is we need to find the distance from this point to this point. So in specific, like this distance. Okay, so in an FCC structure, like we know, there will be atoms and phases also, but like half atoms in each phases also. So we need to consider that one also. So here, like looking this figure, you can see that this dimension is A and this dimension is A, and we need to find this direction. This is same as this direction. So this finding this direction, like we will get a square plus a square is equal to this much, 4r square, and on substituting and solving, we will get the value as this. We have already done in this previous slides. Now again, the total radius in this particular direction. Okay, we will take this direction as this one, because in cube all the sides are same, so we can take this one. So the total radius in 110 direction, total radius here up to here it's r, and from here to this, from this point to this point it is 2r, so 3r plus r is 4r, and the total radius we got it as 4r, and one atom, we can say one atom will be 2r, one atom will be 2r, 2 times the radius. So we in the number of atom lies in 110 direction, that is 4r will be in terms of direction, in terms of atoms it will be 4r by 2r, which is 2 atoms. 2 atoms are lying in this from here to here, so we will take it as 1. So the diagonal length of that unit cell, we know it is a, and a square plus a square is equal to, we will take it as x. So x square is equal to a square plus a square. So we will get the value as the root 2 a, the root 2 a. So dividing this equation, that is 1 by 2, that is number of atoms by the diagonal length, okay, 2 by root 2a, and where a is 0.405. So I'm substituting this one, you will get the value, or you will get the answer as 3.5 atoms per nanometer. So that is the linear density of this particular problem. Okay. Now let us see what is a planar density and how it can be calculated. The planar density of 110 plane, and on solving we will get the plane as like this. Okay, so the plane will be this will be the plane. So this will be the plane, and we can calculate the planar density of this particular. And for easy representation, I am taking it in this fashion, like A, B, C, D, E, and F. It will look like this. So now we need to calculate the density. As we know, first we need to calculate the area of the plane. So since it is a square or square plane, we can calculate the value it as AC into AD. Okay, since it is let's say okay, we can say it's a rectangular plane. We can say the value was AC into AD. So what is AC? Okay, we have seen from our earlier figure that the diagonal value, okay, diagonal value, it will be like r plus 2r plus r. In terms of radius, you can say the value is 4r, and the edge length AD, which is equal to a, and in terms of r, in terms of radius, we can tell it as 2 root 2r. Okay. So totally AC into AD is 8 root 2 r square in terms of radius. I am taking in terms of radius, but sometimes for university problem they will give the radius and they will ask to solve it. And here we need to calculate the number of atoms present in the here. So here, like it is very important. Here actually we will in our volume aspect, okay, in our volume aspect, or the volume, the contribution of the atom, we will take a three-dimensional. In three-dimensional view, this particular atom will act as 1 by 8. The contribution will be 1 by 8. But here, as mentioned here for calculating the planar densities, there is a slight change there. Okay. So I am considering this as my plane. Okay, so here I have one atom, here I have another atom, here I have one atom, here I have another atom, here I have another atom, and finally here I am having another atom. So we can just see the contribution, because in earlier case it was a three-dimensional aspect, but here it is only two-dimensional. Here actually we need to find the contribution, that is, so in two-dimensional it will be 1 by 4, here 1 by 4, 1 by 4, and here it is 1 by 4. Okay, and here it will be half. So in order to clearly explain this concept, I will just draw a neat figure, and I will show you how it looks like. Okay, now let us take a plane like this. So we want to calculate how much atoms are present here. So here a quarter will be there, another half will be there, another quarter will be there. Here again same, another quarter will be there, another half will be there, another quarter will be there. So in effect, if we consider a plane like this, it will be like as shown here: A, B, C, D, E, and F. If we see the contribution, let us see the contribution. Now let's see the contribution. Here the contribution will be 1 by 4, here it will be 1 by 4, here it will be 1 by 4 of an atom, and here it will be 1 by 4. Okay. And some center to center atoms is also there. I am going to draw the center atom. So here you can see half contributions there and half contributions there. So it is very important that you need to have this concept. Here don't take the atom as 1 by 8, because it is not three-dimensional view, it is just a two-dimensional view. Okay. So the total will be like the quarter atoms will contribute some 1 by 4. So the total number of atoms like will be 1 by 4 into 4, because 4 atoms will be there, plus, and the and here and center atoms will be half into 2. So altogether we can say that total number of atoms present in this particular thing, or in particular the density for density calculation will be here 1 plus 1, which is equal to 2. So that we have taken it as 2 here and divided by the area which we have calculated. So sometimes in university questions the radius will be given and you will be asked to find the thing, or the planar density at a particular plane. So you can proceed in this. So that's all for this video. Thank you for your kind attention.